We're working our way toward analyzing RLC circuits. But before we do that, we have to discuss one of the tools that's important in analyzing AC circuits: phasor diagrams. What we're doing with this phasor diagram is treating the voltage and the current sort of like vectors. Not quite. We call them phasors. They have a magnitude and a direction associated with them. So if I plot a vector here, the length of this vector is equal to V maximum, and the projection of this vector onto the vertical axis gives me the voltage across my device at this instant in time. So this vector I drew, V maximum, rotates around and around, and at any instant in time, if I look at a projection onto the vertical axis, I know the instantaneous voltage on my device. So if I started at t equals 0 with my V maximum vector pointed along the horizontal axis, there'd be no voltage on my device at that instant. And as it sweeps out through the first quadrant, eventually I get to a point where I have my maximum voltage across my device. And then it reduces again. Remember, this is an AC circuit. Eventually, it would go back to 0 voltage on my device. And then I'd end up a little short time later with the maximum voltage in the opposite direction, current flowing the opposite direction. And then a short time later, we'd be back where we started, and the cycle would repeat. And we can do this with both voltage and current. We can also draw a vector here that represents the current, and the projection onto the vertical axis would be the instantaneous current through our device. These phasor representations of voltage and current rotate with a constant angular speed omega. And at any given time, omega times t gives us the location, the angle that that vector makes with the horizontal axis. These phasor diagrams are useful in analyzing AC circuits because the voltage and the current don't always hit their maximum values at the same time. So let's take a closer look at resistors, capacitors, and inductors in AC circuits. Here's our simple circuit with an AC power source and a resistor. And we know that V is equal to IR for a resistive device. And if we just solve for the current, we get it's proportional to the voltage being supplied to the resistor. The current is directly proportional to the voltage. When the voltage hits its maximum value, the current also hits its maximum value. When the voltage is 0, the current is 0. So in a phasor diagram, we draw the voltage with this orange line here, and the current with that blue arrow, and they point in the exact same direction. They are said to be in phase. When one hits its maximum value, the other one hits the maximum value also. And the projection of those vectors onto the vertical axis gives us the value of the voltage across the resistor at that instant in time, or the value of the current through the resistor at that instant in time. With a capacitor, it's a little more complicated. We know that Q equals CV, and I is dQ dt. So we have to take a derivative to get our current, a derivative of sine omega t. That gives us a cosine function, and we know that the cosine of omega t is the same as sine of omega t plus pi over 2. The cosine of theta is equal to sine of theta plus pi over 2. That means that the current is shifted by pi over 2 from the voltage. It doesn't hit its maximum value at the same time as the voltage hits its maximum value, like they do in a resistor. So for the capacitor, we get a graph that looks like this. The voltage and the current don't hit their maximum values at the same time. They are shifted. We say that the current leads the voltage because we have this plus pi over 2 here. We say it leads the voltage. And if we draw them in a phasor diagram, the voltage points in this direction, and our current leads by 90 degrees. It's 90 degrees ahead of the potential. In an inductor, the voltage is L di dt. That means we're integrating in order to find the current in our circuit. Using the identity from earlier to get from cosine back to sine gets us to this point. The current, V maximum over omega L times sine of omega t minus pi over 2. So for the inductor, we say it lags the voltage. The current and the voltage hit their maximum values at different times, but the current is behind the voltage this time. In the capacitive circuit, it was ahead. Again, with the phasor diagram, once we draw in the potential difference on the device, on our inductor, we would get the current lags, is behind the voltage phasor by 90 degrees. And the old saying that was always introduced to us when I was in school is Eli the Iceman. And this is a mnemonic that's used to remember which one lags and which one leads. So for an inductor, in a circuit where we have an inductor, the voltage leads the current. We have the voltage on this side and the current on that side. The voltage comes before the current, leads the current. But in a capacitor, the current, it comes before the EMF, the potential. Current leads voltage in a capacitor circuit. So maybe that'll help you remember which one is which in these circuits. Eli the Iceman. You might be wondering what an Iceman is. In the old days, before refrigerators, people had in their homes what was called an ice box. There's a section underneath where they'd put a big chunk of ice, a big cube of ice, and the section above would stay fairly cool. They could keep their food in there for a longer period of time than they could without that ice. So it was kind of an insulated cooler built into the house sometimes. Sometimes it was standalone. And a delivery person would come by and bring a block of ice to you every week or so, and that person was the Iceman. So you got a little history lesson also. Let's take a look at an RLC circuit, a resistor, an inductor, and a capacitor in series in one circuit. We know that our resistor, the current and the voltage are in phase. Here's a phasor diagram that represents a resistor. The inductor, the current lags the voltage by 90 degrees. And in a capacitor, the current leads the voltage by 90 degrees. But there's one thing we know about a series circuit. The current is the same for every device in series. So we can align the three current vectors, and when we do that, we get this phasor diagram on the left. All three currents align, so the current we can just leave the way it is. It's fine the way it is. But these three voltages, we want to know the voltage at any given time. We can combine them into a single vector using simple vector addition. The inductor and the capacitor just point in opposite directions. So we could form a single vector here that's just the potential across the inductor minus the potential across the capacitor. And then we need to use vector addition to figure out what the sum of the last two are. When we add these two vectors, we get the hypotenuse of this triangle. So our maximum voltage now points in this direction, and it makes an angle with respect to I maximum. That's not 90 degrees. It's some other angle. It depends on our circuit. It depends on the value of our C and L. First, let's take a look at this relationship. We know that the voltage across the resistor is IR, and the voltage across an inductor is I times X sub L, and the voltage across the capacitor is I times X sub C, the reactance of the capacitor times the current, and the reactance of the inductor times its current. So we can combine these, and we can get an expression for V maximum and I. Your book works through more of the details if you want to see that, but you end up with an expression V maximum is I maximum times this quantity, the square root of R squared minus X sub L minus X sub C squared. And we know that this is in that form, V equals IR, or V equals I times the reactance for devices that have reactance. And so for this circuit, it's a combination of reactance and resistance. We call it impedance. The impedance of the circuit. It's a combination of the resistance of the resistor and the reactance of the inductor and the capacitor. In our next video, we'll look at solving a simple RLC circuit problem.